It's for me a great pleasure to introduce Professor Christian Wüthrich. Christian Wüthrich is an associate professor in philosophy of science at the University of Geneva. He's a leading scholar in the field of philosophical foundations of quantum gravity. And Christian has already been a speaker at the Urbino School, and I would like to thank him for accepting our new invitation. So please, Christian, you have the floor.
Thank you very much, Pierluigi, for the very nice introduction, and thanks to all the organizers, Enzo, Marco, Enrico included, and I'm not sure whether there are others as well, but thank you very much for setting this up and for inviting me. As every other speaker said so far, I think it's too bad we can't do this in person. It would have been even better than it is already, but it is what it is, and let's try to make the best out of it. So today I'm going to talk about sort of 2.5 papers, or try to present basically the content of about 2.5 papers I've written, and they concern the idea of how to possibly confirm whether or not black holes are indeed thermodynamic objects, and more specifically, whether astrophysical black holes radiate as Hawking predicted. Okay, okay. Now, what got me started on this project is one thing I noticed working in quantum gravity. As Pierluigi said, this is where I do most of my work, the philosophical foundations of quantum gravity. I noticed that there is radical and sometimes very vocal disagreement about the goals, the methods, the background assumptions. Pretty much anything is up for grabs in quantum gravity, and physicists really vehemently argue about all these aspects of quantum gravity. However, there seems to be one thing that everybody seems to be agreeing on, and it is the fact, apparently, that black holes are thermodynamic objects. Everybody agrees that black hole thermodynamics is a fact, and that it's something that any fundamental theory of quantum gravity will have to reproduce. In fact, it counts among one of the most remarkable successes of string theory that in a particular state counting kind of argument, you can reproduce, at least for a sort of a very limited class of black holes, the Einstein-Hawking formula for the entropy of black holes, and loop quantum gravity in a very different argument, but also sort of a state counting argument. You get, for a much wider class of black holes, a result that the same formula can be derived, even though there, in that case, it's only up to a proportionality factor, and it's not so clear how to actually fix that proportionality there. But both camps, as vehemently as they disagree about everything else, have celebrated their partial success in this respect as among the biggest reasons why their research programs are viable. Okay, now this robustness of consensus, as you could say, the universality of the consensus, to use other terms we've used this week in other contexts, is really curious, particularly because it's not as if this is something that has been observed and this has been empirically confirmed. So when quantum mechanics was developed, for instance, there was a wide consensus as to which empirical results had to be reproduced, because there were some empirical results that had directly to be reproduced. But this is not the situation here. We have no empirical confirmation of Bekenstein entropy or of thermodynamic behavior of black holes in the usual way. So this is an interesting situation. Should get any philosopher interested, I think. So on what basis rests this substantive agreement here? So I'm going to have two main parts in my presentation today. The first part will be a little bit briefer, and it concerns Bekenstein's original argument from his thesis and from his articles in 1972 and 1973, when he first argued that black holes are thermodynamic objects and that they have an entropy. So I'm going to revisit that, and I'm going to criticize these theoretical arguments as inconclusive. Secondly, I'm going to, and this is going to be the larger part, I'm going to talk about analog gravity and the possibility of perhaps confirming black hole radiation through analog experiments. The first part is based on a paper I've published that has come out 3 years ago in this collection here. I hope you can see that, even though the font is pretty tiny. But I'll post the slides or have Enrico or Marco post the slides afterwards, so you can see that, get the references there. The second part is based on two things, namely a paper that's been forthcoming for, I don't know, at least 2 years, but maybe more. I don't know when it will be published or exactly what's going on, to be honest, but it's forthcoming in Synthese in a collection about non-empirical confirmation that I co-wrote with Karen Crowther and Niels Linnemann. And finally, I'm going to rely on a paper that I'm preparing right now, which addresses some of the criticisms that some people have made of that paper. Okay, good. So at the beginning, Bekenstein makes it very clear in both the 72 and 73 publications that what's the main motivation is some sort of attempt to save the second law of thermodynamics. The second law of thermodynamics is, as I think Eric and maybe others have emphasized, among the most firmly confirmed empirical generalizations that we have in sort of ordinary terrestrial physics, of the kind of physical systems that physicists have been experimenting on for a while. And it appears as if it's possible to violate the second law of thermodynamics by, for instance, throwing a package of entropy into a black hole. And then Bekenstein has argued, sorry, that was the second reference, there seems to be no way for an observer to determine its interior entropy. So whatever the black hole contains, it may contain all sorts of entropy packages that physicists have thrown in over the years or so, but there's no way to determine that because of the event horizon. Therefore, he cannot exclude the possibility that the total entropy of the universe may have decreased in the process. So perhaps, in other words, behind the event horizon, there are anti-thermodynamic processes at work which decrease the entropy of all the entropy packages that we throw into a black hole. And if that's the case, then that would lead to a violation of the second law, in the sense that the total entropy of the universe would then be, which is assumed to be a closed system, would be assumed to be decreasing. So the introduction of a black hole entropy is necessitated by this process. Now, I think this is extraordinarily strong language, even though you may want to save the second law. The fact that the mere possibility of anti-thermodynamic behavior that cannot be observed by an asymptotic observer somehow necessitates the introduction of a black hole entropy seems to be really going, trying to go for a conclusion which is way too strong that you cannot ultimately support by that mere possibility. So, but based on that, Bekenstein says, look, I'm proposing that we generalize the second law to say that the common entropy in the black hole exterior, so the common ordinary usual thermodynamic entropy outside of the black hole has to be added to the, what has to be added to that is the black hole entropy. And the sum of these two never decreases. So that's a generalization of the second law. By the way, I know that some of these things have come up during the summer school, and I am a little bit torn between skipping stuff and repeating things. On the one hand, I don't want to make this too boring. On the other hand, I'm very much thinking of what Jeremy Butterfield once told me. Apparently, Abner Shimoni once said to him, you should never underestimate the pleasure of people experience when they hear things they already know. I'm sorry if you already know that. I'm hoping you have a little bit of pleasure, at least if you do. And I also do that because I was not able to participate in all the lectures this week, so I'm not exactly 100% sure what you all know and what you don't. But I hope I'm going to go sufficiently fast that even those who know all of this won't be too bored. All right. Oh, okay. So Eric tells me it was Fermi, not Abner. Oh, really? Okay. I misremembered then. But it was Jeremy who told me that story. So maybe he misremembered or I would misremembered anyway. It's the Fermi pleasure principle. Okay, right. Yes. Very good. Excellent. So let's assert the Fermi pleasure principle here and continue with this. Okay, but here's the structure of the argument, and maybe you never so systematically thought about that. So hopefully this will be somewhat new. So the idea is that there seems to be, so one more thing. Now, what does Bekenstein do? Bekenstein in '72 is very much impressed by the area theorem that Hawking proved just shortly before that and published in a paper. He has shown that a black hole, the area of a black hole horizon, at least under some relatively physically reasonable assumptions, cannot decrease. So there is an asymmetry. There seems to be somewhat of an arrow, if you want, in there that begs you to pick it up and write and somehow connect it, associate it, put it in analogy with the arrow that you find in the thermodynamical second law. So there seems to be, at least formally speaking, an analogy here between two things. This is, don't look at the details of the formula. This is just supposed to express thermodynamic entropy. There's a quantity, thermodynamic entropy, ordinary thermodynamic entropy, which according to the second law generally increases. And there is a quantity that one can define, which wasn't quite defined in this. So the proportionality factor was not fixed originally by Bekenstein. That was done by Hawking. But it's proportional to the area, that's the relevant thing, of the event horizon, which also increases. So there's two entities, two quantities, I should say. Both seem to increase. Well, they should be the same, right? Well, let's not to be too quick. Of course, Bekenstein also realizes that this is a little bit too quick, and you need some good argument why you should now not just sort of state the formal analogy here between certain properties of the event horizon's area and thermodynamic entropy. So he tries to motivate the physical salience of that analogy, to really convince us that this is a physical analogy, not just some sort of formal analogy. Okay, and the way he does that is by going through information theory. So this is Shannon's entropy, the formula that Claude Shannon found when he discussed information theory. And the Shannon entropy quantifies the uncertainty which is lost by a message. So it's a measure of uncertainty, if you want, or a measure of attenuation in content, as it were, in phone line signals. That was the kind of problem that Shannon was concerned with. And he didn't initially call it entropy. There's the famous story that you probably also know, that von Neumann, when he talked to von Neumann about this, von Neumann told him, you should call this entropy for two reasons, because this actually turns out to have the same mathematical form up to the Boltzmann constant, depending on the units you choose, to Gibbs entropy, which is, in a way, it's based on a statistical micro-physical understanding of thermodynamic entropy. So now you have to replace this object here by a statistical mechanical understanding in which you have microstates with different probabilities. Then you get to the same formula. And of course, von Neumann said this to Shannon, so that would be a reason to call this an entropy as well. And secondly, and that was the joke, nobody knows what entropy really is. So you will always have the advantage in any debate you will be having with anybody else. So, I mean, that's the story. That's the story how Shannon tells it. So Shannon called it entropy. And now Bekenstein thinks if this Shannon entropy is physically really the same kind of thing that this thermodynamic entropy ultimately is, and I can show that this information theoretic entropy is the same thing as this, then by the transitivity of identity or something like this, then I have established that really the area of a black hole's horizon is an entropy, or is proportional to an entropy as well. Okay, now, so if that's successful, that would establish that this is a physically salient connection, not just a formal coincidental analogy. And that's the project that Bekenstein undertakes in much of the 72, 73, these early articles. Now, the problem is, and I'm not going to go into this, if you're interested in the details, you can read my paper. There are reasons to doubt that information theoretic entropy is exactly the same thing as thermodynamic entropy. A thermodynamic entropy concerns some objective facts about the microphysics of physical systems, and how you carve up the microphysics into macro states. That's what's captured not so much by this version of the formula, but by the usual thermodynamic statistical understanding of thermodynamic entropy that you find in Boltzmann and Gibbs, and that has become standard. Here, however, really what this is it's concerning subjective facts about the epistemic state of agents that we're concerned with, and it's not obvious that these are the same things. It's not my project for today to argue whether or not these are the same thing, but there is a literature about this, and there are significant doubts that these are the same thing. And in order to make that argument successful, you would have to establish that these are the same things, and you have to successfully address all the concerns against it, something that Bekenstein doesn't do. So there is a problem with this side of the argument, but I think there's also a problem with the other side here, because it's also not obvious that this information theoretic understanding of entropy, which concerns the subjective epistemic state of an agent, is really the same thing as a quantity, a geometric fact, really, about horizons in general relativity. So this is far from obvious, and the kind of arguments that Bekenstein produces are arguments of the kind, well, you know, if you have an external observer, if something falls into the black hole, of course, then you can't know it anymore. So as for all intents and purposes, it has disappeared for the external observer. Anyway, okay, good. But I mean, at least both of these connections are questionable. And in order to establish them, you have to really address the concerns. As long as you don't do that, I don't think you can really claim that you've established the physical salience of that connection. But if that's the case, then it seems we're back to the weak formal analogy. Well, I think that thermodynamic entropy should be somehow the same thing as an entropy in terms of the surface area of the black hole, of the event horizon of the black hole. Anyway, so that's the first part, questioning this association. And now I'm in good company of having questioned these kind of arguments, because physicists in 1973 and 1974 didn't really buy into Bekenstein's argument and didn't believe that black holes are truly thermodynamic objects. And in fact, Hawking was convinced that they are not, apparently, when he set out to do the calculations he did when he discovered Hawking radiation then. Okay, so far, what we would like to fix here is that if this detour that Bekenstein makes through information theory does not succeed, then his argument fails to establish the physical salience of the otherwise just sort of formal analogy between thermodynamic entropy and the black hole area. Now, there are other ways of confirming that black holes are thermodynamic objects. Thankfully, we don't have to rely on Bekenstein's original arguments. And there are certainly two kinds of arguments, it would seem. And the first are theoretical considerations. And physicists, ever since the period of Bekenstein today, have considered all sorts of theoretical arguments, reasonings. Usually they provide some sort of suggestive thought experiment involving lowering a box containing radiation near the event horizon of a black hole, opening and dropping the radiation and then retrieving the box, things like this, or putting black holes in boxes and subjecting them to some sort of a Carnot cycle, having them equilibrate with their surroundings, the radiation in the box, things like this. So this is a thought experiment that's recently been produced, for instance, by Prunkel and Timpson. And so there's a long history of thinking about black holes thermodynamically that try to establish that black holes are thermodynamic objects. Now, of course, we shouldn't forget, as the sort of the curmudgeon old empiricist would insist that physics is an empirical science, and maybe you could also use empirical confirmation maybe to make the case. Okay, now the problem and the very interesting situation of black hole thermodynamics is, as others have said before, is that both of these routes of confirming black hole thermodynamics are problematic. The first one is that even though these theoretical considerations are very suggestive and they seem to establish the coherence and tenability of black hole thermodynamics, and indeed in often very, very impressive ways, there is absolutely no doubt about that. And in that sense, they can certainly establish the plausibility of the idea that black holes are thermodynamic objects. But I would claim, again, based on some relatively mild empiricist assumptions, I would think that they cannot confirm that it's truly the case that actual black holes in our universe are conclusively, in some reasonable physical sense, thermodynamic objects. And the reason is it's just been too many times in the history of physics that the substantive majority of physicists have been convinced of something, of its plausibility, that they and from its plausibility they've inferred to its truths, only to find then later on that the world doesn't work like this. So the history of physics is full of examples like that. You can start with Aristotelian terrestrial physics of bodies moving to their natural place, to Cartesian attempts to giving mechanistic explanations of all physical processes, to Einstein's complete conviction that the world has to be local, all sorts of things which we've later found to be deeply problematic and almost certainly false of our actual world. So there is a problem if you're too rationalist, as it were, about this. What you really need to ultimately ground your theories in empirical confirmation. That's the problem, or the limitation maybe, of any theoretical arguments that you can produce for that. Now, with black hole empirical confirmation, it's also a bit of a minor problem. And to do that, now this is definitely going to be a slide you've all seen before. So let me rush through this. Black holes are thermodynamics objects. So that's the hypothesis we're interested in here. In particular, we mean by that they have a temperature and an entropy. They radiate through Hawking radiation. And this is the formula for the Bekenstein-Hawking entropy of a black hole. Again, I'm not going to be repeating that. One fact that I would like to remind you to remind, though, is that the black hole radiates, according to Hawking, at infinity, or for an asymptotic observer, with a temperature that's proportional to the inverse of the mass of the black hole. That is extremely important for the empirical confirmation, as we will see on the next slide. But in short, Hawking radiation is black body radiation, or at least that's the way it's usually sort of what's concluded, even though Professor Curiel has given us good reasons to actually nuance this claim earlier this week. But it's radiation at the temperature inversely proportional to the hole's mass. Okay. Now, black hole thermodynamics as a set of ideas certainly exhibits a surprising degree of coherence with established physics, but nevertheless, the central theses remain empirically unconfirmed. Now, it is my conjecture, and this is really just a conjecture, that this remarkable consensus that we find among physicists is based on this surprising degree of coherence of this sort of cluster of ideas, that they all seem to cohere so well, not just with one another, but with physics that is well established in the terrestrial domain, with every other part of physics that is basically well confirmed. And it's for this reason that I think that physicists are basically convinced of its truth. Okay, I've just said that. Now, Raphael Sorkin, and I think when he said that, he articulated what many physicists would agree, would sign on to, namely that Hawking radiation is the best known piece of evidence for the association of the horizon area with entropy, and in fact, ultimately for the whole cluster of ideas of black hole thermodynamics. And one piece of evidence for that claim is that most physicists did not take Bekenstein's original argument seriously before Hawking produced his calculation to show that they radiate. Because classically speaking, in general relativity without any quantum theory, without adding any quantum physics, they don't radiate. They're perfect absorbers, so the only temperature you consistently assign to them would be 0, I suppose. And that seems to be, it seems to be odd that an object like that could equilibrate with other thermodynamic objects in the usual way. Now, I say most physicists, but there are important exceptions. As Eric told you earlier this week, he is one of the exceptions. He's argued that even classically speaking, there are indeed excellent reasons to think of black holes as thermodynamic objects. And that's an interesting argument, but I think it's still the case, sociologically speaking, that most physicists remained unconvinced until Hawking produced his radiation. So in that sense, it's certainly an extremely important piece of the puzzle here. I hope we can agree to that. Okay, good. So the situation changes, as I've said, when Hawking put forth his semi-classical argument to show that black holes radiate. Now, this would mean that then the association between area and entropy, and so of black hole thermodynamics altogether, would stand and fall with Hawking radiation. Fall if it turns out that black holes do not radiate as Hawking predicted, then it seems as if it will be very difficult to maintain that black holes are thermodynamic objects. However, if you could deliver decisive confirmation of Hawking radiation, then that would certainly give an extreme empirical boost to the idea. So the empirical confirmation of Hawking radiation would strongly support this association. So maybe I've said the same things in several ways now, but I hope the main setup is clear here. But now there is one problem, that Hawking radiation of astrophysical black holes, of the kind of black holes that we expect to find, for instance, in the center of galaxies, of our galaxy, Sagittarius A star, for instance, and similar black holes, is not detectable in practice. Why is that? Well, as Professor Curiel said earlier this week, black holes are cool. He meant this in a somewhat different way, I take it, but they're really, really cold, thermodynamically speaking, in the sense that the radiation of any significant black hole, of any significant mass, is tiny. Because it goes with 1 over m, it means that for a black hole of solar mass, we have something of 10 to the minus 8 to 10 to the minus 7 Kelvin, perhaps. And for the kind of supermassive black holes that you find in a center of a galaxy, maybe you have 10 to the minus 14 Kelvin. I mean, give or take 1 or 2 orders of magnitude, it doesn't matter so much. It's just that these temperatures are tiny. They're too tiny to ever gonna be able to detect, even with a very advanced technology, such a signal against the fluctuations of the cosmic microwave background. That is just not a research project. This is not going to work. So if ever we're going to be able to directly detect Hawking radiation, it would have to be of black holes with a much, much smaller mass than those black holes. And maybe we're lucky enough to find some sort of primordial black holes which are on the verge of completely evaporating, which have become so tiny that they radiate at temperatures that can be detectable and which are close enough, or something like that. But that would require not just good technology, but it would require a bit of luck to be able to find something like that. So that's the problem with the direct empirical confirmation of Hawking radiation. Now, Bill Unruh, 40 years ago, in a very interesting article, proposed instead we should look at analog systems, such as the way sound propagates in a fluid. So if you have a fluid which has a certain velocity, is in flux at a certain velocity, and that velocity increases, you get to a point where it will exceed the propagation speed of sound in that liquid, right? And if that's the case, then you effectively have a horizon in that system, because any sonic signals which would have been sent from behind that horizon could never make it outside of that horizon, to the asymptotic observer outside of that horizon. So there are ways of constructing systems which are analog systems in the sense that they're clearly not black holes. They're physically very different systems, which nevertheless may show exactly the relevant kind of analog behavior. So that idea was put forth and substantiated in that article by Bill Unruh of 40 years ago. Now, initially, not much happened, but in recent years, this new field of analog gravity, of trying to study these analog systems in labs, has really become a very active industry indeed. In fact, 5 years ago, Jack Steinhauer has published an article where he stated that he has observed the spontaneous emission of Hawking radiation in analog systems. In his case, it was a Bose-Einstein condensate. As far as I know, that observation has not been reproduced. I don't know why, but this is not all that important for my purposes today. For my purposes today, we can assume that he was successful in doing that. He did observe that analog Hawking radiation. Let's suppose that is really possible, and if it's not been reproduced, it can be reproduced and soon will be. So the basic idea of this project, of this research field is, the basic idea of this analogical reasoning that this idea of Unruh's relies upon is that if two systems are known to be similar in some relevant respects, then we should also be justified in thinking that if we find other behavior in one system, then presumably the other system has that behavior as well. Obviously, that's an inductive argument, not a deductive argument. We cannot be sure that this is the case, but presumably finding some sort of behavior then in one system would increase our credence in, or our confidence in believing that the other system should behave in the same way. Okay, so the central question of analog gravity then is whether these analog models can confirm gravitational Hawking radiation. And with that, I mean whether observing analog Hawking radiation in the lab can in fact confirm the Hawking radiation in the astrophysical context. So in other words, can we learn anything about black holes from these analog models? More generally, can analog models confirm hypotheses regarding inaccessible target systems? The target system here is really the black hole, or rather its Hawking radiation or presumed Hawking radiation. That's something that's inaccessible to direct empirical detection, as I've said. Presumably, I mean, with the exception of maybe we find some sort of, tiny primordial black holes or some other context in which this is possible, but, these exceptions, sparing this, is an inaccessible, empirically inaccessible thing. So can this be done? And 4 years ago, Radin Dordashti, Karim Thébault, and Eric Winsberg published a very interesting article in which they justified this. So it's very interesting. If you actually go and read physicists working in analog gravity, they seem to be thinking that what they're doing potentially confirms astrophysical Hawking radiation, but they usually shy away from bluntly claiming so. Sometimes in the press releases, their university releases that this will be there, but actually when you push them on that, they go like, oh no, I don't know, I'm not sure, I don't want to claim that really. But this article is interesting because this article is very, very clear in defending the possibility that such analog simulation could indeed confer confirmation. That is, give us reason to believe that the particular hypothesis about the inaccessible system, the Hawking radiation in the astrophysical black hole, can be confirmed. This gives us reason to believe that astrophysical black holes Hawking radiate. That's the claim they're making. And here's the main idea how this is supposed to work. So with that, rather than giving you lengthy quotes from their texts, I'm going to try and show basically in one slide how the argument is supposed to work. So here you have the target system. So that's the system you're really ultimately interested in. And that is, of course, black holes. And you ask yourself, do black holes emit Hawking radiation? Radiation of the kind Hawking predicted. Now, there are theoretical descriptions of that target system. In particular, there's a semi-classical model, sort of the modeling assumptions that Hawking made in his calculation. And that model represents that target system, or at least in some of the relevant aspects. That's supposed to be representing that. So that's the side of the black hole. Here we have the side of the analog system. Here we have some different physical system, some Bose-Einstein condensate, some hydrodynamical system, what have you. So there are different kind of systems that physicists are tinkering with. It doesn't matter so much what it is, but you have some analog system, which in some sense is clearly different from a black hole, of course, but nevertheless is described by a model which is relevantly similar to the model that we have of black holes emitting Hawking radiation. So here's, I'm going to talk more about the similarity, these connections here. But the question then is whether those systems emit Hawking radiation, and if they do, then the question is whether they confer the existence of astrophysical Hawking radiation. Now, it's clear that this argument is going to succeed only if two conditions are met. First of all, there has to be what I believe Hempel called a syntactic isomorphism between the models. So the models have to be relevantly isomorphic, or giving us, formal analogies. They have to be formally relevantly similar. And I'm going to accept that for the rest of the argument, because as Unruh has already shown, interestingly, there are some ways of modeling these systems in which there are some partial isomorphisms like that. They're not perfect. There, of course, are also differences. You have to be quite careful, but there are some suggestive similarities, formally speaking. Now, the question is, of course, whether this formal adequacy, or formal similarity, I should say, is indeed physically salient again. Is this more than just a formal similarity, a coincidental formal similarity? And the idea of Dordashti, Thébault, and Winsberg is that, well, we have to assume, of course, that both of these representations here are physically adequate. That is, under the given circumstances we're interested in the relevant approximations, perhaps, and yada, 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 some other sort of, weasel clauses like this model here correctly captures the relevant aspects of the physics of those systems here. And this model here correctly captures the physics or the relevant physics of a black hole. If both of these conditions are given, then they say the second condition here, the adequacy condition, the physical salience of the analogy is also given, and in that case, there is confirmation. So they give actually a several-step procedure, but the first two steps, as you can see here, are assuming that these modeling frameworks we use on both the target side and the analogy side are adequate for modeling the relevant systems they're supposed to be modeling. In particular, in the second step, they assume that for certain purposes and to a certain degree of desired accuracy, the modeling framework MT is adequate for modeling the system T. That's the target system, the black hole, within a certain domain of conditions dt. So in other words, we're assuming that the way Hawking modeled the black hole is the correct way or the adequate way of modeling a black hole. Now, if successful, these steps would establish the physical salience of the otherwise only formal analogy. But the problem is, to repeat again, that in step 2, Dordashti, Tebo, and Winsberg are assuming that black holes are in fact accurately, or they say adequately, described by the modeling framework from which Hawking radiation is derived. And they make this very clear. Here's just one quote to confirm that. So the system of type T again is the target system, the black hole we're interested in. So they say that in this case it's the astrophysical black hole. So, you know, Sagittarius A star or something like that. That's our target system. The modeling framework MT is a semi-classical model for gravity in which we have first, a fixed classical spacetime that features the establishment of an event horizon via gravitational collapse leading to a black hole, and secondly, a quantum scalar field evaluated in the region of past and future null infinity, which are assumed to be Minkowskian. I mean, this is roughly, you've seen this now this week, probably, 10 different times. There's more to be said about the details of these assumptions here of the modeling framework, but more or less, that's what you need. The domain of conditions, dt, is limited to the times after the collapse phase of the black hole. So we look at a stationary black hole, basically. We assume that any details of the gravitational collapse are irrelevant and can therefore be forgotten about. And then the work in dealing with the trans-Planckian problem, which is a problem that would undermine the adequacy of that modeling framework, of course, discussed above. They discussed this earlier in the paper. They think that that work is sufficient to demonstrate the viability of the modeling framework for some further refinements of ds. Sorry, I think that should be dt here. Now, notice that the language becomes weaker and weaker. Here, we're just talking about the viability of the modeling framework. Now, the viability of a modeling framework, I think, is clearly not enough. You could say, well, all sorts of modeling frameworks might be viable for some model. So that's not quite enough. It needs to be at least adequate, or it needs to, in some sense, correctly capture the relevant physics, right? That's what it needs to do. Otherwise, we haven't gained enough. Okay. Now, the problem that Karen, Niels, and I identify in the paper that is still forthcoming, I wonder for how much longer, even though it was written about, I think it was written more than 3 years ago, anyway, is that there's a sort of a problematic circularity in that argument, basically. And that the assumptions that we make are, again, purely theoretical assumptions, so we don't get outside of the sort of the the theoretical considerations and argumentations here really. Now, if it's not known, if the particular modeling framework, whatever its details are of the kind that are required in the astrophysical case to derive Hawking radiation, it's not known whether that actually describes the black hole, black holes in the first place. That's the question we set out to answer. That's what we're interested in figuring out. Is this the right way to think about the black hole, right? Now, this could be confirmed if either we have an experimental verification of that directly. Again, as I said, that's a problem. That's not directly going to be possible. Or here's an interesting other possibility. We have a more fundamental theory, not semi-classical gravity, but some full quantum theory of gravity, which would give us two things. Two conditions would have to be met about that. First, it would be able to derive Hawking radiation. We would be able to derive Hawking radiation or some relevant features of black hole thermodynamics from that fundamental framework. And secondly, we would have independent empirical confirmation for that this is the right kind of theoretical framework.
Sorry, Chris. Nicolo has a question for you.
Yes, can I finish the sentence, please? So that's the indirect confirmation would therefore be also possible if you can, in other experiments, confirm that this model, this fundamental theory is the right kind of fundamental theory of quantum gravity, and you can derive the effect, in that framework, then that would, of course, also establish Hawking radiation. Okay, thank you. So, Nicolo.
Hi.
Hi.
Hi. Do you hear me? Yeah. Mm-hmm. Okay. From this point, we can say that the model from Hawking radiation is a sort of analogy model that we established before in the inductive vision. The circularity is that the model that describes Hawking radiation is an analogy model for describing this situation.
Yes. So if you go back to this picture here, what Tardashti, Thébault, and Winsberg say is we have to assume that this model, basically the modeling assumptions Hawking used to describe a black hole, are the correct ones. They have to assume that to make this a physically salient, a physically relevant connection. And I say that's problematic because this is exactly what we would like to confirm whether or not that's the right way to describe a black hole. So you cannot assume that it is the right way to model a black hole and then say we've confirmed that this is the right way to model a black hole, basically. That's the problematic circularity here.
Thanks for the clarification.
You're very welcome. Okay, now the problem with black hole thermodynamics is that, as I already said, direct empirical verification is not in the cards, but maybe number two would be an interesting situation. Now, the problematic situation here is that there are some candidate theories for a fundamental theory of quantum gravity, of course, and as I've said earlier, some of them have even had some partial success in recovering at least the Bekenstein-Hawking entropy formula to some degree. But you know, all these theories themselves are far from being empirically confirmed. Neither string theory nor loop quantum gravity nor any of the other competitors, they're just far away from being an established fundamental theory on which we could draw then to say that Hawking radiation is confirmed. And this stands in a very stark disanalogy, I think, to the situation with the analog models. For the analog models, we actually have an entire sort of different, levels of more fundamental theories of theoretically describing a Bose-Einstein condensate or a hydrodynamic system. We can do molecular hydrodynamics or, Bogol-Lyubov Bose-Einstein condensate theory. Ultimately, we do some form of quantum field theory, which as a theoretical framework for these kind of systems is extremely well confirmed. I mean, we're not dealing in certainty, we're not mathematicians. That's, of course, we could still be wrong. But, if there's anything we know is that, the standard model of particle physics is as well established a scientific theory as there can be, or as any really, to date in the history of science. So here we have a very firm theoretical control or grasp, of the situation, very much unlike the situation with black holes, where we just don't have any comparable kind of theoretical control. So the grasp on black hole physics is not remotely as firm as that of the analog system considered, which typically terminate in a fundamental theory for which there's independent and substantive empirical confirmation. So in a way, the analog models are doubly in a better situation. First of all, you can directly empirically confirm all sorts of things with them, because you can create them in a lab and do experiments. And moreover, the theories which we use to model them are much more confirmed than in the case of black holes. So that's the bit of a problem. And a way to express the problem is, what we don't know is whether black holes fall into the relevant universality class as the one tested by the tested analog systems. Now, by universality class here, I mean something relatively loose, meaning the class of all physical systems which show the relevantly same behavior that would lead to Hawking radiation. Okay, so we have concluded that by assuming that black holes are accurately described by the modeling framework from which the derivation of Hawking radiation is a necessary consequence, Dardashti, Thébault, and Winsberg already assumed the conclusion that we're trying to establish, that Hawking radiation exists in black holes. And it is in this sense that they're begging the question. Now, they're not begging the question in a deductive sense, that you assume God exists, and from that you get to the conclusion God exists, or something like this. It's not as deductively straightforward as that. These are inductive arguments, so it's an inductive analog, if you want, if you permit the expression, of begging the question. That is what's going on, but it's still a problematic circularity. Now, here's one thing that you could respond, of course, to that, to our conclusion. You could say, like, look, maybe there is no confirmation in the sense that you talk about, but surely we're learning something about astrophysical black holes, at least in the sense that, these experiments in analog gravity, they add plausibility to the hypothesis of gravitational Hawking radiation. As philosophers of science have argued before, analogical reasoning can confer plausibility and in that sense has a heuristic value. Now, I don't doubt that. Of course, it can add plausibility. Of course, it can be of heuristic validity. But as such, it can maybe deliver a proof of concept, right? It can show the coherence of the idea in other systems. It can add plausibility in these all sorts of other ways. But these are ultimately theoretical considerations, even if they involve experimentation, insofar as we believe them to be applicable to black holes. So yeah, again, what we don't have is confirmation. Now, not sure how much time I should spend on this. I have a few more slides to go. Maybe very quickly, in a paper that was published 2 years ago, but was submitted after, or was published after we submitted our article, Dardashti, Thibault, and Winsberg, together with Stefan Hartmann, had a follow-up paper in which they precisified what they really mean by confirmation. And what they really mean in that paper, they said, is a quantitative sense of confirmation, namely the sense of Bayesian confirmation. In Bayesian confirmation, you have a confirmation of a hypothesis H if the posterior probability conditionalized on the evidence is larger than the a priori probability that you would confer on the hypothesis before you make the experiment, as it were, before you get the data. So if the data, if conditionalizing on empirical data increases the probability and therefore presumably the credence you should have in that hypothesis, then you have confirmation in the sense of a Bayesian. That's in a sense relatively weak, because that confirmation, quantitatively speaking, can be tiny, and it can be from 0.0001% to 0.0002% maybe, or something like that. But anyway, that's the concept they have in mind here. And they say, look, what we have is what's called a Bayesian network. I'm not going to present a full theory of Bayesian networks here. That's going to be a little bit too ambitious, but it's a Bayesian network where M, the node here, so you have nodes and you have these arrows, these edges, directed edges between the nodes here. You have M, which represents the modeling framework, the statement that the modeling framework is adequate in the case of the target system, so for the black hole, that's M. And you have A, the same corresponding assumption that the modeling framework you use to describe the analog system is adequate. And you then have the evidence E obtained, so that is, you observe Hawking radiation in the analog system. That's E. And then you have a universality node here. You have the assumption that their universality arguments provide a common background assumption, a set of common background assumptions that hold for both the target system and the analog system. So in other words, you assume that the target system and the analog system both fall in the same universality class. They show the same universal behavior. That's what you assume by putting X here and by making these connections of positive probabilistic relevance. Okay. So it's this X factor which underwrites the universality claim. Now, based on this Bayesian network, Dardashti, Hartmann, Thibault, and Winsberg proved the following theorem, namely the idea that if you make some assumptions about the positive probabilistic dependence for each of these three edges in the network, then you can show that the posterior probability of M here is larger than the a priori probability of M not based on E. So E, therefore, in that sense, increases the probability that M obtains, that you should put in M as a rational Bayesian agent. That's the idea. That's the theorem that they show. But notice that they have to make some assumptions. Of course, it's a theorem. You can't just prove something from nothing. So you have to put something in. And what you assume basically is this network structure with positive probabilistic relevance for the between the nodes. Okay. So among other things, what you assume is that the probability of X given M is larger than the probability of X. So you assert the positive relevance of the universality arguments for the target system. So what you do is you don't claim that you're certain that this is the correct modeling framework. A Bayesian can never assign a credence of 1 or 0 to any hypothesis, to any proposition. It always has to be strictly between the two. So you can be confident, but you cannot be certain in an absolute sense that something is true or false. So you assume that it's possible that this modeling framework is the correct modeling framework, given that we already assumed that M probabilistically depends on X when we drew the edge, when we drew the network initially. Now, we still think this is problematic because even so, you assume, even though only in a probabilistic sense and in a more cautious sense, that the modeling framework is correct, and in that sense, what you like to establish, namely that black holes fall into the relevant universality class. And you could say, but Chris, everything that's required is that you don't completely rule it out, right? You're not allowed to give it a 0 probability, otherwise it's not going to work. So, but surely that seems reasonable, right? And it also seems epistemically responsible to claim that the modeling framework is adequate, the probability that the modeling framework is adequate given that it falls into the universality class surely must be larger than the probability of the modeling framework being adequate if it doesn't fall into the universality class. So it seems this is epistemically responsible, the right sort of sufficiently mild conditions. So what could you possibly object to that? Well, I'm telling you what's there to object to that. It's the problem that it seems to lead to a really problematic conclusion, namely that you can increase the probability of believing in astrophysical astrophysical Hawking radiation as highly as you would like to do by making a long series of terrestrial experiments on systems which are different systems than black holes. Take more and more analog systems, detect Hawking radiation in all of them, and you can get arbitrarily confident that black holes should be those which emit Hawking radiation. Right? Yeah, exactly. So this is one man's modus ponens is another man's modus tollens. So for me, given that this modeling framework leads to this conclusion, which I take to be absurd, that you can ever get arbitrarily confident that black holes emit Hawking radiation without ever looking at black holes seems problematic. So what we're interested in, to repeat, is exactly precisely whether black holes are appropriately modeled in that framework. And in the Bayesian framework, this translates into the question of whether there should be an edge at all between the X and the Y node in the network. Okay, let me give you another example, which is completely unrelated to black holes, that maybe I like to think supports my modus tollens here, I suppose. And it's an example from the philosophy of mind. Now, the central question in the philosophy of mind is, of course, whether you could have artificial intelligence, whether, you know, some sort of machine which is sufficiently advanced and intricate and complicated could develop or have mental states of the same kind as we do. Could you really recreate in some sort of almost mechanical way, by having something like a human brain maybe, sufficiently complicated, of course, sufficiently rich to get mental states? That's really the central question in a way in the philosophy of mind. And as you may know, people have disagreed about what the answer to that question should be. And I'm now telling you, if the Bayesian argument works, we can decide that question without ever having to look at artificial intelligence. This is great news, right? Because, so this is a question whether the whole of China can be conscious, or whether you can have a very complicated system of pipes and water flowing through pipes, a network of pipes, whether that sort of network could create consciousness, right? Or something like that. I mean, pick your favorite sort of artificial system network like this, which has to have a certain complexity, of course. And now the question is whether you should say that this is conscious or not. Now I'm telling you, we're doing Bayesian confirmation theory here. So no one is allowed to give 0 probability or 1 probability of 1 to that hypothesis, right? That say artificial intelligence can be conscious, right? You're not allowed. Pick any number you want, but you're not allowed to pick 0 or 1. Now maybe, you know, a functionalist or some sort of physicalist would take, oh, I'm pretty confident that, you know, with a sufficiently advanced artificial intelligence, we can create consciousness. So I would assign 0.75 or whatever, right? And the dualist would probably say, no, I'm going to assign 0.01 or something like that. Well, it doesn't matter what you assign. By the appropriate network that we can now draw, which is completely the same as in the case of the black hole, and by doing experiments on analog systems, not on artificial intelligence, but I'm telling you, analog systems are human beings. Now, you know, look at human beings. Look at human beings at different ages, different sex, different background, different environments, different whatever, you know, genetic difference you may want. Perform experiments on those, but they all have to be human beings in the sense of, you know, terrestrial analog systems or something like this, and see whether they are conscious or not. And maybe, you know, you conclude after having observed thousands of humans, you conclude, yeah, you know, they're all conscious, right? We have good reason to think they're all conscious. They all show, maybe there's the occasional exception, but most of them show sign of consciousness, right? So each of them, given the huge diversity of them, we should now increase the confidence that the artificial intelligence should also be conscious. Now, I'm asking you, would the dualist accept this as convincingly increasing to any arbitrarily high level the confidence we should have in the hypothesis that you know, artificial intelligence is conscious? I don't think so. I think they will say that, no, look, this is a completely different case. What I protest against is assuming that artificial intelligence falls in the same universality class as the human beings. That's exactly what I protest against. That's exactly what I claim is not the case. And we could only ever find out whether or not I'm right by actually looking at artificial intelligence, not by testing any number of humans, because humans are relevantly different. Or at least, I mean, that's what is at stake between the functionalist and the dualist, right? So this setup seems to presuppose probabilistically that all functionally equivalent systems belong to the consciousness universality class. But of course, as I said, that's precisely what is at stake in the debate. All right, good. So I hope to have shown, or you know, at least made plausible, I suppose, that there is something problematic about using analog gravity and only analog systems to confirm astrophysical Hawking radiation. Now, of course, you know, although the paper is still forthcoming, of course, you know, Thébault and collaborators have read the paper a long time ago, and they have written a response. And in fact, the response is already published, even though our paper is still forthcoming. Yeah, that's the way, you know, philosophy, you know, publishing works in philosophy sometimes. It has appeared last year. It's a paper by Peter Evans and Corinne Thébault, where they consider the limits of experimental knowledge. And in there they say that they come back to this question, and here's a quote from them. They say, our second core claim that they're going to defend is that an experiment of a manipulable and accessible source system of the kind you can have in analog gravity can be, in some circumstances, used to make an inductive inference regarding the target system of a different type. In other words, it can confirm something about the target system of interest. In particular, when we have good reason to believe that the source and target phenomena in question are universal, they fall each within the same universality class, it is possible to make inductive inferences from the existence of the phenomena in the source systems, so that's your lab analog systems, to the existence of the phenomena in the target system, that is, to astrophysical Hawking radiation. Such inferences constitute a new form of intertype uniformity principle, which play a structurally similar role to inductive inference to that played by more standard uniformity principles, space-time intratype, and conventional inductive reasoning. So what do they mean by that in that last sentence? Is probably worth spelling this out. So you probably all know about David Hume, who has famously, at least when he put on the skeptic hat, he produced a sort of an inductive skepticism. He said, you know, how can we ever be sure that, excuse me, if we sort of generalize what we found here and now, or up to date, sorry, my voice is giving in. So it's about generalizing from what you find from your sort of limited spatio-temporal region, right, to all spatio-temporal regions, that the sun will rise tomorrow, that the swans are white, not only in Europe, but also in Australia, and things like this, right? That's spatial and temporal extension. That's conventional inductive reasoning of the kind that Hume questioned. There's also intratype inductive reasoning. You can say that this copper wire conducts electricity, right? And you can say, well, I can infer from that that all copper wires conduct electricity because they're of the same type, the same kind of system, right? So this is conventional. Now, what they say is, what they want to argue is now that there's also another kind of uniformity principle, an intertype uniformity principle. But when you think about it, you realize immediately that you have to be very careful here, because from the fact that copper wires conduct electricity, you cannot infer that any kind of wires conduct electricity, obviously, right? So this is more tricky, but nevertheless, they say under appropriate circumstances, there are inferences of this type, and anyone who doubts this, is skeptical about that kind of inference, is like Hume, a stubborn inductive skeptic. If we don't put to the side, we can never do science in the first place. So in other words, is a sort of a crazy person. And they put us a little bit in that camp because they claim that our argument is basically at the end just inductive skepticism of the boring kind. Anyway, let's go on. So what we're interested in is intertype inductive reasoning, or they call it inductive triangulation, which is basically a sort of a more sophisticated network of inductive inferences. Now, omitting some irrelevant details, as I said, they said that they charge us with expressing unreasonable doubt of the kind of the inductive skeptic. And they, in their argument, they distinguish inductions of two kinds. You can make an inductive inference from a system that is accessible to a system that is inaccessible. And you can make an inductive inference from intratype then to an intertype, that is to types, systems of other types. So that's the kind of inductive inferences we're interested in, because we're interested in whether or not black holes are of the same type as the analog systems, and the analog systems are accessible, yet the black holes are inaccessible in some sense. So the question is whether we can make inductive inferences of these sorts. And here's an example of an intra-type inference. So we're not changing types yet, but we're inferring from accessible systems and the physics of accessible systems to the physics of an inaccessible system. And they argue this to show that it cannot be the inaccessibility itself that is problematic. And for this, they look at stellar nucleosynthesis, which is really a neat example. I applaud them for coming up with a relevant and interesting example here. And so I need to tell you a little bit about stellar nucleosynthesis here to appreciate what's going on. So in main sequence stars, that's a certain category of stars, of which our sun is one, astrophysical theory tells us that there are two principal reactions which transform the hydrogen fuel into helium. And there's the so-called proton-proton chain and the carbon-nitrogen-oxygen cycle. Now, it doesn't matter what the details of the physics of these two reactions are, but it's important that they take place deep within the stellar core. Only there you have the conditions conducive to these reactions. And the relative abundance between the two reactions depends on the varies with the size or the mass actually of the star. Okay, so it's a bit different for different sized stars. Now, certainly both of these processes, both of these reactions are unmanipulable, because we can certainly not directly interfere with them because they're deeply in the core of a star, like of the sun, right? And we cannot manipulate them indirectly by adding vast masses to stars or cutting off some bit of stars so that the relative abundance between the two processes changes or anything like that. They're not manipulable in the usual sense of a system that a physicist has in a lab, of course. And they are inaccessible to us. We cannot look at them. Now, actually, here's a subtlety. They're inaccessible, as they make clear, photonically. So that is, there are no photons which directly come from the interior of the star to us that we could detect. That's true. However, there is actually a neutrino flux from these reactions in the interior, deep in the interior of the sun, that can be observed on Earth. So it's not as if they're completely inaccessible to us. They're, to some limited degree, inaccessible. But anyway, as they rightly say, the inference from the observed phenomena of the stellar surface, and maybe including also the neutrino flux that can be observed, and certainly the observed spectra of the terrestrial atomic systems, of which we have a lot of experience, with which we've certainly tested in many circumstances in terrestrial labs, and nuclear phenomena that we find and can manipulate in terrestrial particle accelerators, in CERN in Geneva, for instance. The theory of stellar nuclear synthesis is really confirmed to a significant degree. There are apparently some people who doubt it. It's not a completely universal acceptance, but it's widely accepted as a very good theory of what happens, how a star of the main sequence fuels their radiation, the energy, what the energy source is. Okay? None of this I can test, to be clear. Okay? Now, let's look at something that's an intertype inference to an inaccessible system, that is of possibly a different type of system that is moreover inaccessible. There is, they say, prima facie, only a fundamental difference between the two forms of inference, that is the case of stellar nucleosynthesis and the case of astrophysical Hawking radiation, if one thinks that there is a fundamental difference in kind between intratype regularity principles, because the sort of processes and reactions that happen inside the sun are of the same kind of the reactions we can to some degree produce in terrestrial physics, and inter-type regularities, where maybe it's doubted that a black hole, an astrophysical black hole, is of the same universality class as the analog systems we're dealing with. Now, they find nothing special about inter-type inductive reasoning that bars inductive triangulation of the usual form based on two observations. So they have two pieces of evidence in support that, in principle, there's nothing problematic about inter-type inductive inferences. And first of all, in many cases, what may appear to you as inter-type reasoning could just as well be intra-type of reasoning. To some degree, it's not a sort of a God-given distinction into kinds or types of systems. To some degree, whether or not a system falls into a kind of system or is a type of such and such a type depends on your theoretical interests you have, on the particular aspects you look at, right? And depending on that, then something may be of the same kind or not. And they say, quite rightly, I think, that they would expect this to be particularly true in the life sciences, but also in molecular and material science. So in the life sciences, if you test, medication on animals, of course, there's always the question whether mice, operate or react in the same way as primates, and so on and so forth. And for some concerns and for some medications, they probably are of the same kind because they have the same kind of, chemical reactions in the nervous system that goes on in a primate as well, and so on and so forth. But in other ways, they're different from primates, right? And for other medication, that may be relevant. So whether or not you consider this of the same kind or not depends really on quite a bit. And there's a sort of a shift between the two. So maybe, we shouldn't give too much to that distinction as well in the case at hand. And moreover, there exist examples of scientists using Wilsonian-type universality arguments to justify inter-type reasoning of this form in a range of condensed matter contexts. So where you have different kinds or different types of systems in condensed matter physics, for which you then use Wilsonian-type arguments to argue that nevertheless you can make an inference from one type of system to another type of system. But as Patricia has convincingly shown on, I think it was on Tuesday, this is a very well controlled theoretical context here. Much more so, arguably, than what we're looking at when we look at black holes. Anyway, let me try to graphically show what they're trying to do. So we both agree, we can test on accessible types and systems of the same kind that make inferences about them. That's pretty unproblematic. Now, one way in which you can go is then to infer from these accessible systems to inaccessible systems of the same kind. That's what we did in stellar nucleosynthesis. You could, of course, also, from accessible systems of the same type, try to make inferences to other accessible systems of a different kind. So you make an inference here to accessible systems, which is, however, an intertype inference. Now, the question is really this box here. If something is inaccessible and at the same time possibly of a different type, can you somehow combine these two operations, these two inferences, to make the diagonal inference? That's the question, right? And they claim absolutely yes. Sorry, horizontal is an inference across the limit of accessibility, and vertical is the inference to other types of systems. And here's what they say, and I'm almost done. Sorry for taking longer than I thought. One final option for interpreting the circularity claim is that we, in our paper, still forthcoming paper, might take there to be an inferential problem specific to inferences based upon the combination of the two, namely that you combine inferences from accessible to inaccessible systems at the same time as you cross, possibly at least, the boundaries of systems of the same kind. The idea might be that there's some problem inherent to this combined inference that is not reducible to either of its components. It is difficult, however, they say, to see how the logic of such reasoning would work. If it is permissible to reason separately from accessible to inaccessible systems and from systems of one type to systems of another, then we need some reason why it is not permissible in principle to reason from accessible systems of one type to inaccessible systems of another type. So long as our inferences obey classical logic, such concatenations must be accepted, they think. There seems to be no room for reasonable doubt. So anybody, in other words, who disagrees with this concatenation of operations, who finds this problematic, is an unreasonable skeptic. Now, first, classical logic is certainly not valid for such inferences because we're talking about induction, not deduction here. So I think it's clear that this classical logic just has no bearing on that. If anything, we would need an inductive logic and see whether inductive logic would in fact permit such a concatenation, but that's far from obviously the case, and there is no well-controlled inductive logic, of course. So there is prima facie no reason to think that the concatenation of two permissible inductive inferences must therefore also be automatically permissible. We have no inductive logic, which gives us a general, permission to do that. Now, these inferences are supposed to confer support or confirmation. That's what we're talking about at the end of the day. And it's precisely the combination of simultaneously inferring from a system that is accessible or from systems that are accessible to systems that are inaccessible at the same time that we're looking at the different type of system, namely a black hole, which is not what we're doing in the lab physics, that seems to make the inference risky. So given the inaccessibility of the system, it's exactly this inaccessibility which precludes us from determining whether the move from intertype systems to intratype systems is problematic or not. If it were accessible, we could do tests. We could figure it out whether this is a problem or not. This is what pharmaceutical companies do when they do animal testing. They have a very good understanding of what works in one context and what kind of inferences does not work across types and so on and so forth. And at the end of the day, they have to do studies with humans as well to make sure that this is a legitimate inference. But this, given the inaccessibility of the system, this is precisely what we cannot do. So we don't know whether there's the same universality class or not. So anyway, this is my last slide, I promise, and then I'm done. So black holes, and this is important when I do make critical remarks here about how well justified we may be for taking black holes to be, thermodynamic objects or not. They may well turn out to be. I'm not a skeptic of that. I'm not saying that this is not the case, not at all. What I'm interested in is figuring out what our epistemic warrant for believing them to be thermodynamic objects, what that warrant is. Establishing that they are, in other words, is what I'm interested in. That, I think, is interestingly non-trivial. There are many arguments, including those by Bekenstein and Hawking, which are somewhat suggestive. There are some really interesting very suggestive arguments out there. They're all theoretical considerations. They all add plausibility to the idea, as do experiments in analog gravity. I don't doubt that at all, but they cannot confer confirmation. They cannot be conclusively, and we should treat them accordingly. So for all its ingenuity, the argument by DTW and the later version of the Bayesian version and the later response by Evans and Thébault and so on and so forth. Thébault has a number of other articles where he covers different aspects, of course, of this. They're all very interesting and very suggestive, but there's a problematic circularity. So the problem then seems to be that the inferential step, the analogy, is ultimately, again, based on theoretical considerations. It could only be based on empirical considerations if either we could directly test black holes, or we could test in some way more fundamental theories, which then would, from which we could derive the behavior of black holes. And then we would have also empirically confirmed indirect understanding and knowledge of black holes. So at the end of the day, what we need is to get firmer constraints on the theorizing in quantum gravity in particular. I mean, at the end of the day, that's what I'm interested in, of course. There's nothing better than ultimately empirical work. So we need to observe black holes. We need to try to learn more about them by observing them in more ways, or other astrophysical objects, or maybe coming up with terrestrial experiments which can test aspects that may be of quantum gravitational importance. So at the end of the day, we need to do astrophysics, maybe also some lab physics, and quantum gravity phenomenology, I'm afraid. So thank you very much.
Thank you so much, Chris, for your very clear and great lecture. And I enjoyed it very much. So the floor is now open to questions. Okay, we have many questions. The order is Katie, please.
Thanks very much, Chris. It was really interesting. I have lots of different questions, but the main thing I want to ask is, so you had at the beginning, you had this analogy between, you had this kind of three-way diagram with the information theoretic entropy at the bottom. And I was wondering whether you, and I completely agree with you, it seems like something very different is going on when that's talking about like subjective uncertainty of agents. I was wondering if instead of the Shannon entropy there, if you had like the Gibbs von Neumann entropy, where you could understand the probabilities not in the usual Janesian way, but instead in some kind of objective way. How you spell that out might depend on your preferred interpretation of quantum mechanics. But nonetheless, it seems like there's like the possibility of understanding that in a more objective way. And I wondered if yes, that entropy formula at the kind of bottom triangle of the diagram, whether that was the Gibbs von Neumann entropy, whether you think then it becomes a bit more persuasive.
Yes, absolutely. No, I completely agree. This would certainly remove a number of very immediate worries when we would replace the Shannon entropy with the von Neumann-Gibbs entropy or something like that, maybe. Absolutely, yes. Because then the whole sort of inference from epistemology to ontology, as it were, would be, from just sort of what agents may be subjectively placed to rationally believe or something like that, to the way the world is objectively, or some objective features about a physical system, that would be that would certainly be improved if we could eliminate that. Absolutely. It's not what Bekenstein does in these early papers. He actually does explicitly talk about Shannon and the sort of information theory that was still relatively young at the time. And I think that's just a non-starter, really. That's not going to give you the arguments, or that's not going to be sufficient to underwrite arguments to the conclusion that black holes are thermodynamic objects with thermodynamic entropy. If anything like that, you should say that, no, look, there are certain objective features of physical systems. If they have those features, then they have a well-defined entropy, as we know from terrestrial systems, and black holes fall into that class. They are objects like this, or should be thought like this. And of course, there's some considerations about that. Most physicists like to sort of the state counting arguments, so they look for some sort of statistical mechanical underpinning of states of either the horizon of the black hole or of the black hole interior with the horizon, or something like that. And then you do some sort of state counting argument, as you do in ordinary thermodynamic objects, and therefore you should get an entropy. This is extremely interesting and suggestive work. Again, if you can make this coherent, and there is certainly suggestive work in that direction, then that can underwrite the plausibility of the claim that we should think of black holes in these terms. But the problem is, how do we ever know that these state kind of counting arguments of black holes are the right way to theorize about black holes, right? That's in a way what I'm interested in. How do we get some sort of empirical confirmation of that? And we would either, again, by directly observing thermodynamic behavior of one kind or another of black holes, or by deriving these sort of things from a more fundamental theory, which is independently confirmed, of course.
Thank you. I'll be quiet. I have more questions, but there's lots of other questions too.
Yes, I have to do other things, like grading final exams, I'm afraid, but I'll try to pay attention to the Slack channel, and I'm certainly going to try and engage there with those of you who will not have time to ask a question now.
Okay. Sarvar?
Yeah, thanks for your talk. Can you hear me well?
Yeah.
Yeah, thank you.
Yep.
So as I understood, you said that if there can be a consensus about like Hawking radiation, then we can accept black holes as thermodynamic objects. So now it seems to me that the problem is Hawking radiation. And then I think from your paper, I gathered that Hawking radiation is somehow, in some sense, is a prediction from quantum field theory. And as you know that black holes are predicted by GR. So now my question is, for accepting a theory by the scientific community, we don't need always to somehow confirm all the predictions. So that some predictions are confirmed and then a theory is accepted, like GR. And then don't you think that if quantum field theory is well confirmed and then GR is well confirmed, it's enough to conclude that that Hawking radiation is the case, and then they are thermodynamical objects?
Okay, good. Yes, I certainly accept that quantum field theory in very many relevant terrestrial or other contexts is well confirmed. GR is well confirmed, spectacularly both in some cases well confirmed. The problem again is now when we're trying to look at black holes, one of them does not seem to be sufficient to establish that black holes are thermodynamic objects. I mean, Eric thinks that GR alone may be sufficient, and that's fair enough. But most physicists would really think, no, you need both. You need GR to have black holes, because without that, you don't have event horizons of the gravitational event horizons. So forget about it if it's just QFT. And you need quantum effects to get Hawking radiation, because if you don't have some sort of quantum field where you have then an event horizon that can cut off modes and anything like this, you don't have Hawking radiation. So you need kind of both. You need to combine them. The problem is, as well confirmed as the two theories are independently in different regimes and for different physical phenomena, we don't really have confirmation for the combination of them in the intersection of the two. This is what's it's really difficult, right? And we know, I mean, quantum gravity seems to be the relevant theory ultimately that we need for two things, right? To describe the very early universe and to describe black holes. That's what most physicists believe. And it's exactly because these two phenomena, if you want, or these two different physical realms are believed to require novel physics, that it is not with any degree of a priori certainty we can assume that the way we combine GQFT is going to be the right way. I think it's eminently plausible again. I'm not suggesting that. I think it's reasonable to expect that there should be the appropriate low energy limit, should be something like a sort of a semi-classical gravity, right, of the way we do. That would be extremely surprising if that's not the right way to the right limit there. So, and because it's really not more than that you need to get Hawking radiation, that's why physicists, I think, are very confident that they're right in thinking that there is Hawking radiation. But nevertheless, the problem is, and I'm looking now again at the principal perspective, black holes seem to require novel physics, and we don't have much of an idea of what that fundamental physics will look like. How could we know that? Well, if we do empirical science of the way we do normally. Either we look at these objects directly and test with them, or observe them, and so on and so forth, or we produce a theory that we can test in other ways, but that would be fundamental and would be applicable directly to that. So if we could, maybe it would be enough to actually have semi-classical gravity and confirm that in some other phenomena for something else, then maybe that would be, would certainly go towards the kind of thing that I have in mind.
Yeah, thanks a lot.
Yeah.
Thanks.
Sure.
Patricia?
Thank you. Can you hear me? Yes.
Yeah.
Yes.
Thank you, Chris, for that. That was very interesting. I think I have a question about the role of universality arguments, and more specifically about the meaning of universality arguments. So if I understood you correctly, you said that in order to have a universality argument, you need to know the elements of the universality class. But I think the goal of universality arguments is precisely to demonstrate which elements are in the universality class. So if you understand universality arguments in that way, as arguments that demonstrate that certain elements like analog black holes and real black holes are in the same universality class, and you combine those arguments with arguments for robustness that show that Hawking radiation, for example, doesn't depend on quantum gravity effects, then why wouldn't you avoid the circularity that you were mentioning? And if you avoid the circularity, then why wouldn't you have at least a theoretical basis for analog experiments? So I don't think that those arguments exist yet, but I think my skepticism is more in practice than in principle.
So no. I think that goes toward in the direction of what I have in mind. So you could have, these universality or universality and robustness arguments in the way you distinguish those. Suppose you have those. How would you get to those arguments? Well, they would be of some sort of some theoretical kind, presumably, showing you, convincing you that the trans-Planckian problem is not a problem, and so on and so forth, right? How would you know that? Well, these would be theoretical arguments resting ultimately on some more fundamental theory. And how would you be confident in that theory? Well, by being confident that this is a good theory, a true theory, which correctly describes these things, which you could only know, however, by doing some kind of experiments, getting some sort of empirical confirmation that this more fundamental theoretical framework is robust and universal of the way required. But if you do that,
not.
I accept. Then you would. Sorry. Yeah. Then you would establish that. But you seem to have something different in mind.
I am just thinking about the possibility of having those arguments that I think don't exist yet, and that those arguments would provide you the theoretical basis for analog experiments without having to wait until we can do experiments directly. Right, so as I said, I don't think those arguments exist yet, so I am on your side in being a little bit skeptical about analog confirmation, but I'm not skeptical in principle. I think we might be able to achieve those. So to build those arguments, to have those arguments without having to do direct confirmation or without having to go to quantum gravity. If we could show that Hawking radiation is robust upon quantum gravity effects, then why would we have to consider quantum gravity in the first place?
Yes, no, that's right. But how could we get to that point? How could we get to the point that we've confirmed that Hawking radiation does not depend on quantum gravity microphysics?
With the kind of arguments that we were looking at, but I think these arguments are not perfect yet. But we might, for example, if you draw the analogy between Hawking radiation and Goldstone bosons, then you have good arguments to think that Hawking radiation would be robust because Goldstone bosons at a certain regime are robust. So you can do an extrapolation, which is theoretical, for the robustness of Hawking radiation.
Right, but so you had I forgot the details, but you had about 5 or 6 of criteria that you looked at, right, in which you scored the arguments, as it were, right? If all of those were satisfied, then I think you would have the case. But one of those conditions was that you have some empirical confirmation.
You're right. Yeah. You're right. That's a good point. I think we would have to think about how to make sense of empirical confirmation without that meaning that you have to do direct empirical confirmation of Hawking radiation, which is virtually impossible. Yeah, I think you need some kind of confirmation which needs to be independent of the analog experiments in order to make sense of those arguments. But I don't think that kind of empirical confirmation needs to imply that we have to do direct experiments to test Hawking radiation in real black holes, because that would make the entire enterprise virtually impossible. But I think I'm a little bit more skeptical only in practice at the moment and not in principle with the possibility of building these arguments.
Yeah, no, I completely agree with you. I think that's it's not required that we have empirical confirmation directly, that sort of in some way directly detect Hawking radiation astrophysical black holes or in some other black holes, maybe primordial black holes or something like this. I don't think that this would be necessary. It would be great if we could do that, but I really don't see how this could be done, except if we're exceptionally lucky or something. And I certainly accept that it could be done otherwise. It could be done indirectly, absolutely, of the kind of arguments that I think you have in mind. But the building blocks of those arguments would have to be otherwise empirically confirmed.
Somehow, yes, I agree.
Some degree of confirmation necessary there to convince us that this is confirmed, or confirms Hawking radiation. But then I would accept, yes, absolutely.
Thank you.
I don't
Thank you.
think we disagree, actually.
Thanks.
Thanks. Eugene?
Hi, can you hear me?
Yeah.
Yes.
All right. Yeah. So just a clarificatory question. I think you mentioned something about let's see, the modeling. Like it's not clear whether like the way Hawking modeled Hawking radiation was like adequate for actual black holes. So I was wondering if you could like say a bit more about like why you think that's the case or something like that. Yeah.
Why I think that the modeling assumptions are correct or not?
I think you mentioned they're like incorrect, or like we don't know whether they're correct.
Right. Yeah. I mean, so the modeling assumptions are basically the assumptions that Hawking or any sort of derivation requires for Hawking radiation, right? So you have to assume an event horizon, you have to have some sort of quantum field, and that's the sort of modeling framework you need. Now, my point is not that I say this is incorrect, but my point is assuming, as at least in the original paper, Dordashti, Thébault, and Winsberg do explicitly, assuming that this is an adequate modeling framework is really circular, because that's in a way the question we want to have confirmed, we want to know about. If we've learned that this is the right way to model black holes, then we've learned something about black holes, but that's exactly what we would like to learn. So we cannot presuppose that. That's the sort of the circularity one worries about. And then this, I think, is attenuated in the Bayesian framework, where this is only, sort of probabilistically assumed with maybe a very low degree of confidence initially. But I think that's still problematic for the reasons I've tried to show as well. So I'm not saying that it's incorrect, definitely not. It may well be the correct way. As I said, again, it's pretty plausible also to me that this is the right way to think about black holes. I would be surprised if black holes would not radiate pretty much like Hawking said they do. But confirming this is more than that. That's the point. Yeah.
All right. Thanks. That clarifies things.
Thanks. The last question, Eric.
Well, I actually have a few more or less trivial remarks, and then a couple of questions that would actually take me a while to formulate. So maybe it's better. Okay. It's best if I just put them on Slack, since it's all after time.
Yeah, I promise to check in on Slack. I'm not sure whether I can do it today, but hopefully tomorrow or Sunday. I mean, this Slack channels are going to remain open even though the summer school terminates today, right?
Mm-hmm.
Yes.
No reason. Okay, good. Yes.
And just to emphasize to everyone, if you are curious, I'll be putting my questions specifically on the Slack channel for Chris's talk that's dedicated to Chris's talk today. And I think that people aren't automatically subscribed to that. You have to go and manually subscribe to that yourself if you want to see that channel.
Yes, and switch off notifications, as I've noticed. Otherwise, you receive an email every 30 minutes or something. Yeah.
Yeah. Well. Thanks again, Chris. And
thank you.
Okay, the school will start again to the 2:30 p.m. and well, thanks again, and see you later.
Thank you very much for having me once again, and I'm afraid I won't be able to participate this afternoon, so I already apologize for that. For reasons I've indicated at the beginning, because we're not physically in Urbino, I sort of organized too many things this week in a way, and that's unfortunate. But I'll follow things on Slack, and I'll look at the slides and the videos.
Thanks.
So thank you very much.